two more talks today. First off, we have Vasileios. He's coming to us from a postdoc at Chicago, but he did his PhD at Cornell, and he's actually starting at UW-ECE in the fall, which we're very excited about. And so I am very excited about what he works on these days.
Yeah, thanks so much. Yeah, thanks everybody. Thank you to the organizers for the invitation. So yeah, I'm super excited to be talking about this inverse scattering problem today. And I want to start by acknowledging my amazing collaborators. So these are all UChicago people. And I do want to highlight Owen, who was the main driver of this work. He was the PhD student basically behind this whole project. OK. OK, so what is inverse scattering? So let me start with maybe a motivating example. So imagine you're like a geological survey company, and you have a client that says, I want to understand what is hiding under the seabed. Okay? So you have some options. One of them is to just start digging. Terrible idea, waste of money, resources. You may not discover anything useful. So here's another way to do it. You deploy a bunch of hydrophones. So these are basically like sensors. And then you emit a bunch of shock waves with an air gun. Those waves travel through the seabed. They penetrate this medium of interest. They do their own thing in there. So basically, the way they travel is modulated by the properties of the material. And then eventually, they get reflected back up. And so you capture them on your load sensors. OK, so always I guess most of the time, in inverse scattering problems, there's this notion of like an inhomogeneous medium that you're trying to probe in a non-invasive or non-destructive way. OK? So let me make this a little bit more mathematically precise, but I'm going to abstract it away. Basically, what's happening is we have a scattering potential Q. So this is a function with some domain of interest omega. So you have the spatial variable x, and the values of this function tell you how conductive this material is, if you're talking about electromagnetic scattering, or they tell you like how dense the rock is, or some property that you care about. Okay? The way you probe it is you have some simple waves that you throw at it. So in this case, we have these complex exponentials. But basically, the idea is you have a number of source directions, s. These are usually just like uniform on the unit circle or something. And then each probe wave is actually associated with some spatial frequency k. So typically, you need to do this for many, many different wavelengths to actually understand your material well. And another thing is we assume that outside the domain of interest, everything travels at a constant speed. So all of these things are functionally similar outside of the domain of interest. OK, so this is how you probe the material. The second aspect that's important is actually what are the physics of the problem like. OK, so basically what happens is as soon as your probe waves penetrate the medium of interest, they start getting scattered. So they might get deflected off of different objects. They might bifurcate. They might do all sorts of things. But sort of the punchline here is that the mapping from the scattering potential Q to the particular scattered wave is actually a highly nonlinear mapping. And I want to give you a little bit of a scare by showing you what is the actual equation that describes this relationship. So there's this equation called the Lippmann-Schwinger integral equation. There's a Green's function involved because it's actually it's the solution of an underlying Helmholtz PDE. But I don't think it takes that much time to convince yourself that this is sort of a difficult mapping to write down. So now we have some idea about the physics of the problem. Let me just tell you about the measurements and how you collect them. Basically, what you can assume is that you have sort of like a ring of very large radius that is enclosing the domain of interest. And you have a bunch of receiver directions. So these receiver directions tell you where the sensors are placed. So what you end up measuring is the scattered wave across these different locations. And you have to do this for each incoming direction S and each receiver direction R. So what you end up collecting in the end is all of these what we call far field data, which is the scattered wave measured across all of these receivers for all the spatial frequencies for which you probe this material. Okay? Here's what it looks like in case you're curious. So you start with some scatterer Q. It has this sort of toy shape that I'll come back to later. And you can see here and here, we have measurements at different spatial frequencies. So the spatial frequency actually changes drastically what your measurements look like. Okay, but I guess the point in all of these applications is you have some far field data that you collect, and the point is to recover this scattering potential Q. So it's basically an instance of an inverse problem. All right? Okay. Any questions so far? All right. Let me move forward. When you're trying to solve this problem, it looks scary, and most of the time it is, but there's certain cases that we can simplify it a lot. So one of these cases is what we call the single scattering regime. And what this functionally corresponds to is basically taking a Taylor expansion of this forward mapping, calligraphic FK of Q, and just saying, OK, this is approximately linear. Right? So this is not always a good assumption to make, but in certain cases it's plausible. So I want to use this scary-looking equation to demonstrate it. So one instance where this is plausible is when your scattering potential Q actually has low contrast, which means that most of its values are small. Right? Another instance is when the scattering potential Q is mostly 0. Right? This is what we call scatterers with narrow spatial support. And then finally, there's another instance where the wave number K is small. So we're talking about low frequency waves. So these are not perfect. This is not a perfect approximation, but these are 3 cases where it kind of makes sense. Right? You can get something useful out of it. So having this linear approximation down, what we can do is we can just solve the associated linear inverse problem. Right? So this gives rise to an algorithm called filter back projection. It's the bread and butter of many signal recovery methods. So basically what you're doing is you're inverting those measurements, and because of things like ill conditioning, you have to add a little bit of regularization. Right? But this is the algorithm. Super simple. It's not even an algorithm. OK. Something that's important is that when you do a kind of perturbative analysis of this forward model, if you're working in the right coordinate bases, you can represent this filtering operator approximately by 2-dimensional convolution. And then you could represent this adjoint application, which is what we call the back projection, more or less with a 1-dimensional convolution. Right? So even though you might be in a regime where you have high contrast data, right, in which case this algorithm will not do well, you can think, OK, I have a 2-dimensional convolutional representation, and then I have a 1-dimensional convolutional representation. I can sort of make these more flexible. So I can make these maybe neural networks and hope that the nonlinear corrections inherent in those neural networks will account for the modeling mismatch. Okay, and indeed, this is the idea behind lots of recent work that is inspired by the single scattering regime, right? So it's drawing like architectural ideas from the single scattering regime, but is hoping essentially that the extra flexibility afforded by making this a neural network with nonlinear stuff will do a little bit better. Okay, so there's this classical, I guess I call it classical. It's a very recent paper, but it replaces the one-dimensional, it replaces the back projection operator with a trainable 1D convolutional neural network, and it does the same thing for the filtering operator. There's some related work in this area that basically tries to enforce additional, usually hierarchical structure on these convolutions so that it's a little bit more physically plausible. But unfortunately, this is not enough. So all of these approaches still struggle with high contrast data. Or, for example, with scattering potentials that have inhomogeneous backgrounds. All right, so what's the interesting regime? Basically, it's the regime where all of these things are no longer true. So it's cases where the signal has high contrast, wide spatial support, or you have like high wave numbers k. So let's take a step back and try to think what we would do if we had no idea about the particular physics of the scattering problem. Right, so let's put on an optimizer hat. How do you solve inverse problems as an optimizer? Well, you just write down some penalty, right? Let's say L2 squared penalty. Here's this penalty for the inverse scattering problem. Basically, you're trying to minimize the mismatch in the measurement space, okay? And you're optimizing over some plausible set of scattering potentials. This is very non-convex. I'll show you like a toy example that I think demonstrates this. So you have to deal with all the intricacies of non-convexity. So you have to deal with spurious local minima, stationary points that are not useful, like condition numbers are horrible, all of that stuff actually comes into play. So maybe you can ask yourself, as an optimizer who wants to do something useful, how do you avoid bad solutions when you're solving this optimization problem? Right? So you could cheat and just ask for a very good initial guess. Or you could think something better, which is if you have measurements at multiple frequencies, right, so at multiple wave numbers k, you know from the single scattering regime that actually the relationship there is linear. So it's almost the same as if you're solving a convex quadratic program. So this yields a natural idea, which is how about we use low frequency estimates, starting from some sufficiently low frequency, to get basically reasonable initial solutions for higher frequency subproblems. Okay, so I'm going to return to this idea in just a second. I just want to show you like a toy example that demonstrates the non-convexity as sort of the way the problem changes qualitatively as you go through different wave numbers k. Right, so let's look at a very simple family of scattering potentials. So we parameterize them as Gaussian bumps. So what is happening here is that your scattering potential has some unknown amplitude. So you only need to determine a single scalar beta. And the bandwidth of the Gaussian bump is, let's say, known to you. All right?
Are they all centered at the same place?
Sorry, what was that?
Are they all centered at the same place?
Yeah, yeah. But the thing you want to figure out is just the amplitude. So here's what this looks like as you go from 4 pi wave number all the way to 32 pi. Okay? You have this very nice looking bowl for the low frequencies, and then as you increase the frequency, gets more and more. The thing gets more and more oscillatory. And this is sort of a contrived example because here it's enough to just solve the low wave number and you're done. But this is not the case with real world scattering problems. Okay, so I alluded to this idea before, which was how do we use low frequency, or let's use low frequency estimates to initialize some algorithm that's solving higher frequency subproblems. So this is the idea behind like a very standard algorithm that is called recursive linearization. So what you end up doing is, first of all, you collect all of your data, right? So you have some collection of frequencies, let's say K1, K2, all the way to Kn. All right, and by convention, I'm going to say like K1 is the lowest frequency that I have. So I'm going to get an initial estimate Q hat K1 just by using this filter back projection method, right? If I do believe that the derivation is correct, and if K1 is low enough that I'm in the single scattering regime, this should give me a reasonable estimate. And then for all the subsequent frequencies, sequentially from K2 all the way to Kn, what I'm going to do is I'm going to linearize my model. So I'm going to do Gauss-Newton steps, where the point that I linearize is the solution to the previous subproblem, but I'm actually using the forward model at the next available frequency. All right, and this is sort of how this algorithm evolves.
From Gauss-Newton?
It's literally Gauss-Newton. I guess maybe one subtle difference is that you don't need to do multiple, or maybe you need to do, I don't know. But you don't do multiple steps for each frequency. You just do one step per frequency. Does it make sense?
Yeah.
Okay. All right. So this algorithm, if all you care about is like high accuracy, it's very effective. It gives you high resolution estimates. Unfortunately, there's something quite unsatisfying about it, which is that it's very computationally expensive. And the reason it's computationally expensive is that for each wave number k and each direction, each receiver direction, you need to solve basically a PDE. Just to evaluate this forward model, you're solving a PDE. And even worse, you need to compute those Jacobian vector products, which involve like another PDE. More unsatisfying, more unsatisfying properties of this algorithm, it's actually very brittle to the frequency spacing that you use. So just in this range, let's say, to go from 2 pi to 32 pi, right? That was the data that I showed before. You need to use 277 frequencies that takes over 40 hours to recover just a single test image. So unless you make your frequency spacing really, really small, this algorithm may not even converge. So this is sort of where like our work comes in. What we aim to do is we aim to design an ML-based approach, so something that involves ultimately neural networks, but actually something that tries to emulate this recursive linearization method. So it's sort of faithful to this idea of going from low to high frequencies. So let me tell you a little bit about that. There's two key features of this recursive linearization idea that we want to maintain. So one of them is this progressive refinement idea, which is that you not only do you estimate the output is not a single estimate of your scattering potential. It's actually a whole sequence of estimates. And you progressively refine them as more and more data are introduced. And of course, the direction at which you do this is important. So you need to go from low to high frequencies. So you can think of it as a homotopy through frequency method. And the key thing here that we want to ensure in our model or in the architecture that we use is that updates at step t contain high frequency information relative to whatever estimate I have at kt minus 1. So our proposal is actually a whole family of neural networks. We call them EMPHIS nets for multi-frequency inverse scattering. Don't yell. It's a composition of refinement blocks. So these are all trainable convolutional networks. And the key idea is that we're doing something special to guide successive blocks to basically perform this homotopy through frequency. So let me show you just like the pseudocode. It's not very interesting. You just start with an initial estimate from filtered back projection, and then you have a cascade of those refinement blocks. And each of those refinement blocks has its own trainable parameters. And of course, the inputs are the estimate at the previous frequency and the measurements at the next frequency. But sort of the key question here is how should this refinement block actually look like? Like not all architectures are equally useful. And we have sort of a mildly satisfying answer based on its practical performance. So let me show you what that looks like. So what we end up doing is we have some previous estimate k hat of kt minus 1. And we have some measurements at the next available frequency. So the first thing we do is we use this FYNet architecture, which is the single scattering inspired neural network idea, to produce a weak estimate of the scattering potential at the next frequency. And then we concatenate this previous estimate with the new like rough estimate in two separate channels. And then we jointly filter them with an additional two-dimensional convolutional layer. And then, of course, we want to maintain the frequency information in the previous estimate. So we just have a residual connection here that essentially adds those two things together. The next question is this enough? Like, what do you do to train this? So one naive thing you could do is you could just cascade all of these things together and just train them end to end. So you say, OK, I want the final output to match my scattering potential, and that's it. But that's it's a little bit unsatisfying because you're not using any of the intermediate information, and you're not using the multi-scale structure of your data and your measurements at all. So there's another, I guess this is the main innovation, which is how do we actually train it? So the idea is we're going to pre-train all of these neural network blocks from coarse-defined scales, and we're going to take advantage of the fact that when you have measurements at a specific frequency, the reconstructions that you can get from those measurements are necessarily band limited. What this means is that if you have measurements up to frequency, let's say 8 times pi, you should not expect a resolution better than some natural frequency associated with that. So what you can do is for each scattering potential in your data set, you can generate a whole sequence of low-pass filtered versions of the scattering potential, and then use them to guide each layer separately. So what we end up doing in practice is, OK, we start with these measurements at the lowest available frequency. That gives us an initial estimate Q hat K1. And we first pre-train this so that it matches the coarsest level approximation of the ground truth scattering potential. Right? So we do this until convergence or until some suitable criterion is satisfied. And then we take this estimate and the measurements at the next frequency. We pass them through one of these refinement blocks. That should hopefully give us an estimate with better resolution. So let's just use the next finest approximation to the scattering potential to train this. And then again, we freeze all the weights in the previous stages, and then we keep adding refinement blocks until we basically have exhausted the amount of available frequencies. All right, and then there's a final step, which is a fine-tuning step that says, OK, now let's unfreeze all of the parameters jointly, and let's just make sure that the last output is actually matching the unfiltered scattering potential. Right, so this final step is not the only step, but it takes like a relatively small fraction of the overall training time. Is this clear? Yeah.
Are these blocks all the same architecture, same size and everything?
I think so, yeah. So this one and this one have the same architecture, but they're using, of course, different parameters. Yeah.
Where do the training targets come from?
So these are part of your data set, right? So you have pairs of scattering potentials and measurements, right? And you can generate those training targets by just doing like some Gaussian low-pass filter. It doesn't have to be exactly what you would get after. Like it's not exactly the projection to the set of band-limited signals, right? It's just an approximation that we have. Right. Any other questions? All right. The next, I guess, maybe 10 minutes of this talk is basically all pictures, tables, experimental evaluations. So I want to start by plugging our data set. So we actually generated a new data set to do a thorough evaluation of this architecture. You can download it from Zenodo. It's in Hadoop file format, because the files actually end up being really, really huge. But the main thing is that it has wider spatial support than existing benchmarks, and the contrast is actually much higher, right? Because we really need to push all of these methods that rely on the single scattering regime and make them fail to design something interesting. And the way they look is a random selection of geometric shapes, so triangles, squares, ellipses, overlaid on a smoothly varying background. So this is what a sample from an existing benchmark looks like. So it's just very simple squares overlaid on a completely homogeneous background. And this is what a sample from our data set looks like. So it's like a ball with, it almost looks like magma or something. And you overlay those shapes on top of it. And if you look at the color bars, you will notice that the contrast here is 0.2, here it's 2, so it's a 10 times multiplicative difference. All right, let me tell you how we do our experimental evaluation. So we actually generate, we use data sets with different frequencies. So we have 5 frequencies total, and we generate a version of a data set that has 10,000 samples at frequency 32 pi. Then there's a version of the data set that's 5,000 samples at frequency 16 pi and 5,000 samples at frequency 32 pi. And then and so on and so on. So basically, the idea is that we want to make sure that the total number of measurements does not depend on the amount of frequencies that you use. It should always be 10,000 samples total that get shown to your network. And then we compare a bunch of different methods. So the first two methods are actually inspired by the single scattering regime. One of them is this FYNet that I showed you before. The second one is this wideband butterfly network that involves some ideas from sparse linear algebra and hierarchical representations. And then we have a bunch of EmphaSnet implementations, two of which are just naive baselines. So the most naive thing you could do here is you could have a bunch of different FYNets for all your different frequencies and then just mash them all together and do some kind of mixing. So I think this is what is called EmphaSnet fused. But really, the method that we care about is this EmphaSnet refinement method that has all of these like architectural and training novelties incorporated. So let me first show you some reconstructions, I guess one reconstruction. So this is a ground truth scattering potential from our data set. This is the reconstruction that you get from one of these previous methods inspired by the single scattering regime. And you can kind of clearly see that there's not a lot of spatial resolution. The background is all wrong. It's not even clear what shape this should be. They're all just basically blobs. But when you use this new method that incorporates measurements at 3 different frequencies and this sort of homotopy through frequency idea, you get much better spatial resolution. And you can kind of tell that, you know, this is not a ball. This should be a square. So visually, at least, this seems to be doing something interesting. And you can sort of also arrive at the same conclusion by looking at the residual images. Right? So these are actually errors between the ground truth and the solution that you produce. The next thing I want to show you is actually a table, like a more formal and systematic evaluation. It's sort of complicated because there's different versions of the data set. So just pay attention to this number. This is one of the methods we're competing with that gives you a relative error 0.261. This line, which is this wideband butterfly network, this actually gets fed 3 times 3,333 samples because it's fusing different frequencies. It's doing a little bit better than this. But even our baselines are already better. And when you look at which one is the best, or which method is the best, it's always the refinement idea that uses this homotopy through frequency. Another takeaway here is that actually using multi-scale data helps. Right? So as you go from like 2 frequencies to 5 frequencies, you're doing more and more. You're approaching the ground truth better and better. Let me just maybe belabor this point again. This standard recursive linearization method is actually really, really slow. Right? Like I told you before, it requires 277 forward model evaluations in serial for each new sample that you present it with. The only case that we do forward model evaluations is to actually generate the data set. So these evaluations do not happen at test time. Right? And when you look at the amount of time that it takes to do all of these, obviously we win, but it's because we don't do any forward model solves. Another thing that I like about this method is that you may have noticed that the frequency spacing is not that small. You go from 2 pi to 4 pi, and then you double it every time. Like it's not a regular grid of frequencies. Whereas when you use some of these algorithms, you need to be really, really careful about how you arrange the frequencies. The last thing I want to show you is actually some experimental evidence that everything that I talked to you about today is actually useful. Right? So it has the flavor of an ablation study. And the question that it's trying to answer is what is actually responsible for the performance gains? So there's 2 things you could do differently here. One of them is you could get rid of the sequential pre-training. So you could still use these intermediate reconstructions and penalize them being bad somehow. So this is what this loss function is trying to do. But you could just train everything end-to-end. So you would do essentially no pre-training. The second thing you could do differently is you could just throw away those intermediate reconstructions, even though we kind of suspect this wouldn't be a good idea. So what we do to test this is we train another network that has the same architecture, but actually doesn't use any of the intermediate reconstructions in the loss function. And again, I have a table for that. Ignore these two lines. Basically, all you need to see is that as you get rid of some of these individual components, you're doing worse. So without sequential pre-training, you increase the error by a little bit. Without progressive refinement, you also increase it. And then maybe you're thinking, OK, but these are all within a standard deviation of each other. This is a little bit subtle, but if you did like a scatter plot, comparing the full method with any of the ablations, everything would be above the x equals y line. So the standard deviations are the same. But when you look at individual samples, you almost always produce worse predictions when you take away those methodological refinements, I guess, from the architecture. Any questions so far? All right. Let me talk a little bit about some ongoing work that we're doing since we posted this paper online. So I want to revisit this recursive linearization idea, right? So the question here is, why are these traditional methods so expensive? What can we actually do to accelerate them, right? And the obvious computational bottleneck that I identified before is sort of this evaluation of the forward model and its Jacobian, right? So the reason why this is expensive is, like I alluded to before, this forward model is a solution of a PDE. And even Jacobian vector products or vector Jacobian products involve like associated PDEs that are basically the same difficulty. Okay? So one natural question here is, it's 2025. We have GPUs. We have TPUs, if that's your flavor. We have basically a whole bunch of hardware that's really good at doing specific things, basically matrix vector products. So can we take advantage of these hardware accelerators to design better solvers for this problem? And the answer, I think, used to be no, until maybe last year. So this is a slide where I just do advertisement for my collaborators' work. But there's this very nice solver called JAX HPS, which is a modern take on a method called HPS from hierarchical Poincare Steklov. And the nice thing about the solver that Owen wrote is not only is it super fast, because it takes advantage of matrix vector multiplications through the GPU, but you can actually autodiff through it. So if you're really, really ambitious, you can imagine you could just put it in a neural network and hope something useful happens. All right, so let me tell you two things that we're actually looking into right now. One of them is this idea that I just described, which is maybe having a differentiable forward map will let us integrate it better with some of these neural network solutions. So maybe instead of using this FY trainable 1D convolutions, maybe we can just plug in the solver and have more fidelity in the forward model. And I don't have any results today. This is something that's it's sort of a work in progress. It's sort of not obvious how to do it best. But I do want to talk a little bit about accelerating some classical recovery methods. So everything I'm going to say today applies to the proximal gradient method, but you can imagine using some of the same ideas for like a Gauss-Newton type method. Right, so I'm going to focus on a low overhead method that uses accelerated proximal gradient. And to make sure everybody's on the same page, I want to tell you what the proximal gradient method is doing. So when you have an optimization problem like this, which is the sum of a data fidelity term that is usually differentiable and a regularization term that is usually non-differentiable, you can't just do gradient or subgradient descent. That's usually a bad idea. What you can do is you can use a local model that only takes the Taylor expansion of the smooth part and maintains the non-smooth part. Right? So this is how you end up with this update, this proximal gradient update. And the proximal operator basically evaluates a subproblem that includes a linear function plus some non-differentiable, non-smooth mapping. So in the context of inverse scattering, the way you would apply this framework is you would set the data fidelity term to be the measurement mismatch. This happens to be a continuously differentiable loss function. And for many, many applications of interest, what you want is actually signals with smoothly varying backgrounds. So a standard regularizer for this purpose is the total variation norm in 2 dimensions. So we're using this 2D anisotropic total variation formulation. Now, there's some issues with that. The first issue is that, well, there's no analytical formulation for evaluating this proximal operator unless you're in a 1-dimensional case. Most problems in inverse scattering are not in 1 dimension. And the second thing, which is the main source of computational burden, is actually evaluating the forward model or the data fidelity term and its gradient, which involves a Jacobian vector product. So there's some past work. I'm naming one of the available solvers, but lots of past work have the same flavor. What it ends up doing is it numerically approximates those gradients using something called the truncated Born series, which you can think of as a glorified Taylor expansion. But having this GPU-accelerated solver, what we can do is we can compute exact gradients, right? We can compute this f of q and the gradient f of q really, really quickly and sort of at high accuracies. And then we also put on top a simple splitting method to evaluate this proximal operator of the total variation norm. And the key benefit afforded by not using an approximation anymore is that we can use much, much larger step sizes than previous work. So there's not necessarily like methodological novelty here. It's just sort of saying that if you have the right tool, do not forget about the fundamentals. So let me show you maybe one reconstruction. So this is going to be like in a slightly different setting. It's going to be an actual data set from the Institut Fresnel in France. And this is electromagnetic scattering. So you have far field data at 4 gigahertz. And the reconstruction that I will show you is initialized at 0 with some pre-specified error tolerance. So this is what the target looks like. This is a 2-dimensional slice of 2 beams. Think of them as pool noodles made from different materials. So you're looking at them from the top and taking a 2-dimensional slice. This is the reconstruction that we get with our method. And this is a 1-dimensional cross-section across this reconstruction. And on the bottom, what I'm showing you is the band-limited projection, which is in some sense the best you could hope for in terms of reconstruction quality. So obviously, we have more artifacts, but it's actually pretty close to the ideal reconstruction. And then when you compare, I don't have a reconstruction from this Sizer method, but I do have a comparison. And when I show you the comparison, maybe it will be clear why I didn't include a reconstruction. So here I'm comparing this Sizer algorithm. This is the past work with our proposal, which is using this accelerated HPS solver on top of the accelerated proximal gradient method. And on the left, I'm comparing relative error as a function of the number of iterations that you do. And on the right, I have the relative error as a function of the cumulative time that it takes to run the algorithm. So not only does the competing method flatten out at a much higher relative error, it also takes a huge amount of time to even get there. In terms of iterations, it's a little bit, the difference is more subtle. But the point is that even with the Born approximation to the gradient of the data fidelity loss, it takes much, much longer to get there. And the dashed line, in case you're curious, is the error that you would achieve by just doing the band-limited projection. So this is best possible. So it looks pretty good. You reap all the benefits of using a GPU. It's actually a very nice story, and hopefully will be online on arXiv in maybe 2 months. I assume Owen will see this talk eventually. So anyway, I want to conclude by sort of telling you what I showed you today again. So I showed you a neural network architecture inspired by recursive linearization that gave us some really nice properties. So first of all, we could do high-resolution recovery without test time PD solves, which is where you get all of this benefits in the inference time, quote unquote. And then because of these architectural ideas and this sort of like new training method, you can actually leverage the multi-scale nature of your data to stabilize the training procedure. And then I also talked to you about some ongoing and future work. I wish I had more on integrating the forward model with neural network solutions, because it's actually a very exciting idea. But I'll just stop here and take any questions.
So you opened up the talk with this motivation of, oil and trying to see what's under the ground. And a lot of these benchmarks seem like very like toy shapes and things.
Yeah.
How does this stuff transfer to? I mean, it seems like the motivational applications seem much more complicated.
Yeah, that's sort of always true, right? You're always a little bit more ambitious than what you can actually do. But for example, with recursive linearization, you do actually solve like real problems. So getting there, so this is something you cannot do with a neural network yet, unless you have like lots and lots of, high fidelity training data. But this is something you could do with the proximal gradient idea. It's just that we don't have a data set or the bandwidth. I guess we should have the bandwidth eventually to try it with real data. Yeah.
So it's a limitation of.
It's a limitation. It's like computational limitations. You probably have to do something a little bit smarter when you go to a real data set in terms of how you arrange all these computation, but I think the key ideas would be the same. Yeah.
Presumably they do something today.
They do something today. So what they do today, I don't want to guess too much. I would assume it's something related to recursive linearization, and maybe they're reusing some computation in a smart way. Yeah.
Naively, so at the beginning you mentioned that this high contrast regime is the difficult one, or is more difficult for previous methods. And naively, as a layperson, I found that a little counterintuitive, because I thought high contrast means signals very different for background. So is there any kind of intuition?
Yeah, so the reason why high contrast hurts is because you get more interactions as soon as the wave penetrates the material. So if everything is flat, in some sense it's easier if everything is flat, because you don't need to know that much. Like, you don't get any interactions. Basically, waves just go in and come out, and that's it.